And here we are, 7.5, compound events and some extra examples. Go ahead and copy down that. So this is your OR probability formula. And it's P of A or B equals P of A plus P of B minus P of A and B, where P of A and B is the intersection of A and B. So what I did was I used colors, and we know that when we mix yellow and blue, we make green. And that's what the intersection of A and B shows right here. So this is your sample space, S. And all your probabilities lie within the sample space. Some of the probabilities lie within A, some of the probabilities lie within B. Some of the probabilities, however, lie between A and B. So then why do you subtract the intersection out? Well, if I'm trying to find the probability of A or B, what happens is this green section gets counted twice. We don't want to count that twice. So what we do is we subtract out the intersection so that it only gets counted one time. Because the way probability works, is you're trying to find this area and this area, but the area gets overlapped. That's why, it gets counted twice. So we'll see how to apply this to a word problem. Go ahead and copy this one down. So, for example, of 3,510 drivers surveyed, 1,950 were male and 103 were colorblind. Only 6 of the colorblind drivers were female. What is the probability that a driver was a male or colorblind? So, one way you can do this, one way people like to do this is, first off, notice this is an OR problem. That is such a key word to this problem. And so, when you see the word OR, it should prompt you to maybe make a Venn diagram. Doesn't need to be anything too fancy, but we're going to make this a rectangle like before. We'll go ahead and make 2 overlapping circles. Because we're trying to find a probability that the driver was male or colorblind, we're going to label these circles male and colorblind. Which, I just realized it's ironic that I'm using a green marker, and green is one of those colors that colorblind people struggle with. Anyways, now all the males, which there's 1,950, would go in this circle. But I'm not going to put 1,950 right here because some of those 1,950 go in the intersection of the two. Same thing with the 103. 103 would take up this whole circle, but I'm not going to write 103 right here because some of those are going to go in the intersection. Some of the colorblind people are male also, but some of them are not male. Now let's think about what we have here. Of the 103 colorblind, they tell us that 6 are female. We can use a little logic here and deduce that if there's 6 female colorblind drivers, then how many are male? We'll subtract, and 103 minus 6 is 97. And so that tells us how many go in the middle right here. So there's 97 that are male and colorblind. It's really important that we know that. Now, how many are just male that are not colorblind? Well, we do 1,950 minus the intersection. If we do 1,950 minus 97, we get 1,853. And so that number would go right here. We could also determine how many are colorblind that are not male, but we already know that. That's 6. All right, so here's how we do this. In this case, I'm going to switch colors here. In this case, if we go by the formula, A is male and B is colorblind. So the formula was P of A or B. And the formula said P of A plus P of B. So what's the probability of male? Well, how many males are there total? There's not 1,950 over the total amount of drivers, which was 3,510. We're going to add the probability of being colorblind. If you go to the problem, there were 103 total colorblind. And then, just like we said, we have to subtract out the intersection. So we have to subtract out 97. Okay? So, luckily for us, because we're adding and subtracting fractions, we need a common denominator. We're lucky that we already have that. So, all we have to do really is get out a calculator. I didn't bring my graphing today, but all we have to do is add up 1950 plus 103 and subtract out 97. That gives us 1956 over 3510. And that's our probability. We can either reduce it, but actually we're just going to go ahead and give a decimal. So if you divide that by 3510, we get 0.5573. That's our probability of selecting a male or someone that's colorblind. So again, we were subtracting out the overlap of the two, of the male and the colorblind. So that's what OR probability questions look like. Again, you'll know it's OR if you see that keyword OR. All right. Now here's some additional examples. Go ahead and copy this down. This one says, what is the probability that a point chosen within this rectangle is within the shaded region? So you have the big rectangle, and then you have the shaded region that's inside the rectangle. So what do we need to do? Well, how much of this rectangle does the shaded portion take up, area-wise? So this is basically an area problem. Well, how do you find the area of a small rectangle? The area, to recall, is length times width. So what's the length and width of this rectangle right here? Well, it's 6 high, but how wide is this? So let's use a little geometry here. We know that rectangles, if this side is 12, then this side is 12. And they tell me that this little section right here is 4, and this little section right here is 4. So 4 plus 4 is 8. That means that this must be the remaining 4, so this is also 4 inches. We can deduce that. So the shaded region is 4 inches by 6 inches, which is an area of 24 inches squared. Now, what about the whole rectangle? What about the whole thing? What's the area of that? Well, it's a 10 by 12 rectangle. So 10 inches by 12 inches, which is 120 inches squared. So to find the probability that you would land within the shaded region, you just put what you're looking for over the total. That's how probability works. So the probability is 24 inches squared divided by 120 inches squared. And we just reduce fractions like we know to. The inches squareds will reduce. They're gone. 24 and 120. Actually, 24 goes into 120, and I'll prove it to you because you may not believe me. Goes in there 5 times. So 24 goes into 24 one time. 24 goes into 120 5 times. So there's a 1 in 5 chance on this figure, which obviously is not drawn to scale at all, would land within the shaded region. And then one more example. What is the probability that from a standard deck of 52 cards, and I'm talking about cards like these, you draw a card at random that is black and has a number on it. So let's think about, there's 2 colors. There's red or black. And we want to know, all the black cards have a number on it. Like, for example, see these cards right here, the Jack, the Queens. These don't have numbers on them. They have letters on them. But, here's some black cards that have numbers on them, like the 6 and the 10. So let's think about, with the deck of cards, there's 2, 3. Remember, there's no 1 in the deck of cards, and we're not counting ace as 1. So 2, 3, 4, 5, 6, 7, 8, and 9. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 total. And that's for any one suit. So this is for any one suit. For example, like clubs. But how many black suits are there? There's 2 black suits. There's clubs and spades. And by the way, I'm talking about this because not everybody knows about cards. So this is, when we talk about suits, that's what a club is. That's that shape right there. Spade is Sorry, I just got a little tangled up here. Spade is that shape right there. So there's clubs, there's spades. There's also on the red, there's diamond and there's hearts. So, anyways, clubs contains 8 of these, and so do spades. So how many is that total? That's 16. And then how many total cards are in a deck? Well, we just said there's 52 cards. And we just reduced this. So I believe 4 goes into both of these numbers. 4 out of 16 is 4. 52 divided by 4 is 13. So you have a 4 in 13 chance of drawing a card that is both black and has a number on it. So how do you make an even... Sorry, how do you make 7 an even number? You take the S out of it. That's funny. A few shout-outs. My boy Adrian, period 2. We share the same name, although my middle name's Adrian. Period 6, they wanted me to shout them out. You guys are a special bunch. And Daniela Racinos, she's the best actress ever. I feel like I'm starting some kind of war saying that between people. I guess we'll find out. Anyways, this is the end of probability. There you go.